I guess I didn't have that much left to cover in the sigmatropic rearrangement. So we'll just make this one quick before we move on to the next reactions. No point in making a video unnecessarily long with like 5 different topics. Okay, so what I want to talk about now is is classifying sigmatropic rearrangements. Classifying sigmatropic rearrangements. So the Cope and the Claisen reactions are examples. Let me say the Claisen rearrangements. I about said reactions. Are examples of 3-3 sigmatropic rearrangements. 3, 3 in brackets. Sigmatropic rearrangements. And so the way I like to think about how to classify these things is if we have our pi system that's undergoing a sigmatropic rearrangement, and let's make the degenerate case the example at hand. So equilibrium constant's 1. Okay, so what I do is I cut the molecule in half, and then I count the number of atoms that are on either half. So I have 1, 2, 3, 1, 2, 3 across the sort of atoms that are broken and formed. That is to say, I've cut across here because this is my sigma bond broken. And the other side, these are the 2 atoms where sigma bond forms. So that's where so you count the atoms on either side, and you could get different numbers too. And I think you typically go lowest to highest. So let's look at another example of a sigmatropic rearrangement. By far, 3-3 sigmatropic rearrangements, in particular Cope-Claisen rearrangements, are the most prevalent and the most likely to be encountered. Most of the time, any sigmatropic rearrangement that we do see in the universe is an example of that, but there are some offshoots. So let's say this is an example from the book. So in this case, what we're actually going to do is consider an equilibrium, that is a rearrangement equilibrium, where we go from having an sp3 hybridized carbon as sort of the rightmost carbon to the lower rightmost carbon. And the lower rightmost carbon now has 2 hydrogens, just to emphasize that, and maybe I'll do this. It could be on either side. It's a symmetric, the molecule's got some bilateral symmetry in it. Okay, anyway, so what's happening here? Well, the pi bond here is grabbing the hydrogen. The carbon hydrogen electrons are coming down to make a new bond, and this pi bond is moving over to fill a hole and make sure no octets are getting broken. So if that's the case, if that's how we're going to break and make bonds, then we're breaking this carbon hydrogen bond, which means you've got 1, 2, 3, 4, 5 atoms between the bond being broken and the bond being formed. That is, the hydrogen is the only element on one side of the bond forming and bond breaking. So it's just 1, in which case this is a 1,5 sigmatropic rearrangement. So you can have these like migration reactions, I guess, that are considered to be pericyclic in mechanism, in which case they would be examples of the movement of one atom by way of a sigmatropic rearrangement. Now, the numbers within the brackets don't always have to add up to 6. We could look at 2-3 sigmatropic rearrangements. Sigmatropic rearrangements. And so an example from the book is if we have a system with a sulfoxide, we could consider an equilibrium between the sulfoxide and what's called the sulfenic ether, or sulfenyl ether, sulfenic ether. Anyway, sulfenic ester. So, but sulfur oxidation states get some interesting names and some hard E's in various places. Okay, so the arrow is here. So we're going to form a bond between these two elements, come down, and then we're going to dump electrons onto the sulfur atom. And so the bond formation, bond breaking is across here. Now within the transition state, we have 1, 2, 3 on this side, and then 1, 2 on this side. So it's a 2-3 sigmatropic rearrangement. And there's a few examples of this. But these are just examples of sigmatropic rearrangements. Again, 3-3 is the most prevalent by far. You can do some Illid transformations with charges present in the molecule that can give rise to other types of rearrangements. But this is how you classify these things, and hopefully this helps us kind of understand these. For a lot of these, beyond the 3-3 sigmatropic rearrangement, they're kind of one-offs, and it just makes sense to practice them as needed. But anyway, that'll do it for the, I guess, part 2 of the sigmatropic rearrangements.